Good morning, good afternoon, good evening, depending on where you are. Thanks for joining me for this Construx Lunch and Learn, Applying Software Estimation Principles to the Coronavirus Pandemic. So I'm Steve McConnell. I'm best known as the author of Code Complete, More Effective Agile. Today, the role that's probably most relevant for me is author of Software Estimation, Demystifying the Black Art. As a numbers guy, you can imagine I've been looking at the coronavirus numbers with quite a bit of interest and trying to understand them. I've put a fair amount of work into that, and I think you'll see some of that throughout the rest of the presentation. And hopefully, if you haven't put a huge amount of work into it yourself, you may get a better understanding of what the numbers mean as well. We've been doing these lunch and learn presentations for over a month now. Back in 2009, during the Great Recession, we offered a SPEAR program, which offered free training to laid off software workers. The lunch and learn program is our attempt to provide something useful for software individuals and teams to do while an awful lot of people are working from home. So at this point, we're going to continue these into May, since it looks like much of the US anyway is still going to be working from home throughout the rest of April and into May, and encourage you to share the information about these lunch and learn sessions with your friends, and encourage people to attend. Let's see. So these lunch and learns were conceived as chalk talks, and I think a lot of the presentations have been fairly scripted and maybe somewhat formal and polished. This one, it is not very scripted, and it's not very formal or very polished. You're basically going to be watching me kind of thinking out loud. I've put an outline together so you can see that. But I think this is kind of appropriate. I mean, we're at a point in the stay-at-home phase where I've cut my own hair. I'm sure some of you have done that as well. And so a little bit of a less formal presentation seems like it kind of fits at this point in time. So let me make sure that everything is set up here the way I want it to be set up, and I think it is. Right. So I'm going to start with an observation, which is that is really based on my work in software estimation, that it's useful if estimators know something about estimation. And the reality here is that most estimates, at least in software, are created by subject matter experts. And subject matter experts tend to use simple, and I would actually say primitive, estimation techniques, even when their expertise in the subject they're estimating is high. And I think that we have seen a lot of that in the numbers that have been reported about the COVID-19, where we have lots of subject matter experts, and we have lots of self-appointed subject matter experts, but we don't have a lot of people who are experts in estimation. And so that ends up being a factor in the numbers that are being presented and reported and analyzed, and in some cases used for policy-making decisions. This is not a talk about policy, and it's not a talk about politics, but I do have the belief that people should make decisions on the basis of clear and accurate numbers. So this is a talk about trying to get to some clarity and accuracy in the numbers. So using better estimation techniques where we know what we're talking about is one point. A second observation I'm going to make is that it's useful to know what subject you're talking about. And this is not a question of expertise. I'm not saying it's useful to be an expert in the subject. Of course, that's useful too. I'm saying it's useful to even know what the topic is. And I think a lot of the numbers that have been presented, people don't even know what topic they're talking about. They throw labels around, they throw numbers around, they think the labels are attached to the numbers, and they really aren't. I'll give you some very specific examples of that. I think by the end of the session, you'll see that we really do lack significant clarity in the conversations about this particular pandemic. Terminology matters, and there's just lots of confusion about terminology. People are using words to mean things that other people think they understand, but that really don't, in some cases, really don't mean anything. And then I will make that should be observation 3, which is that a lot of time rates and trends are more informative than raw numbers. and so we'll get into that a little bit too. So I want to start by clarifying a little bit of estimation terminology. And the word estimate itself is a good place to start. An estimate is an analytical prediction of the quantity of something. Now, most significantly, an estimate can be about past, present, or future. And sometimes people think that it's only one of those. But if we're estimating the number of fish in a pond, kind of a classic statistics problem, that's an estimation of the present. If we are estimating the population of the world in 2025, that's really an estimate of the future. If we're trying to estimate the number of people who died from Spanish flu in 1918, that's an estimate about the past. So we can estimate in either in any of the past, present, or future. Now, sometimes we use the word forecast, and in software world, I think the forecast word has taken on sort of a life of its own. But really, all the word forecast means is an estimate that concerns the future. And so, in our topic for today, we really have both estimation. We do have some estimation about the present that's relevant, and then we also have some forecasting or estimation about the future that's also relevant. So why don't we start with CFR? There's been a lot of discussion of CFR, or case fatality rate, and I think that's a pretty good entree. Well, A, it's a really important topic, and B, it's a really good entree into lots of the issues that are involved in the numbers that are being presented and understanding of those numbers. So I'm going to bring up a couple of spreadsheets here, and let me make sure that you can see those. It looks like you can. And I need to adjust my camera here a little bit so I can see my screen. Okay. So I want to start with a discussion of the absolute wrong way to calculate case fatality rate, or CFR. And what we typically see in published reports is, if you can, let's see if I can get my marker going here. If you can see the writing on the right side of the screen here, it may be kind of small, but we typically see published reports, meaning mostly news reports, calculating case fatality rate as the number of deaths divided by the number of infections. So using yesterday's data, which is the most recent data available in entirety anyway, we had 54,881 deaths divided by 988,000 infections, and that gives us a case fatality rate of 5.6%. And I'm calling this a junk CFR, and I'm being pretty strict about that terminology with myself, because it's not correct, it's not accurate, it's actually a completely invalid way to calculate CFR. But you can find this in all kinds of places. You can find websites that list this junk CFR by country and that rank order the CFR is calculated in this way. And part of the problem with this CFR is that we've had this notion that comes up in software estimation of anchoring effect. And what the anchoring effect says is that initial estimates, no matter how poorly founded, no matter how weak the analysis is or non-existent the analysis is, tend to serve as an anchor against which all later estimates are compared. And in the case of COVID-19, we had an anchoring effect from the initial numbers that came out of Wuhan and the WHO numbers that were associated with that. And those Wuhan numbers were in the 3.5% range. And so we now have this anchoring effect where lots of people are thinking, oh, the number's kind of sort of in the 3.5% range. And so when this junk CFR of 5.6% gets reported, then people get concerned about that and say, oh, it looks like it's higher than the Wuhan number. The real issue here is this is such a completely invalid way to calculate the CFR that the number is basically meaningless, and the real number could be vastly different. By vastly, I mean it could be 2 orders of magnitude different. It could be more than 2 orders of magnitude different in principle. So let me go ahead and erase that. So let's talk about the first correction we need to make. The first correction we need to make is that the idea that we're going to take some cumulative number of deaths, as shown here by the red bars, and divide it by some cumulative number of positive tests and get a case fatality rate just doesn't make any sense if we're talking about the same day. And the reason for that is that the number of people who are infected today, who are test positive today, aren't done getting sick yet. If, for sake of argument, we had 0 positive tests reported tomorrow and the next day and the next day and the next day, that wouldn't be the end of the deaths, because we've still got time that needs to elapse for people to get sick and then get really sick, and then actually pass away. So what we need to account for is the idea that this is a process where there's a lag between getting infected or coming in contact with the virus, then having an incubation period, then developing symptoms, and then making the decision to get tested, and then waiting for the test results, and then for the test results to get reported to whatever agency ends up reporting them, so I can put them in a graph like this, and then people get really sick and then they pass away. And so in terms of the graph here, steps number 1 through 4 all happen before the person even gets tested. They come in contact, they have an incubation period, they have symptoms. At some point, they decide they're going to get tested, and the test results come back. And I'm identifying that as test number, the test results come back in 5, and then in number 6, the test results are reported somewhere. And then there's some elapsed time that occurs before people, as they get really sick and they go into the hospital in most cases, and eventually they pass away. And each of these things takes time. Interestingly enough, there's some randomness in each of these things. The amount of time it takes for someone to develop symptoms is there's some variability in that. The number of people who decide to get tested, there's some variability in that. The time between the test being performed and the results coming out, there's some variability in that. The amount of time it takes someone to go from getting tested to getting really sick and then actually dying, there's some randomness in that. So what we have statistically, when we have a whole bunch of interacting sources or particularly additive sources of randomness, is we have what would be called multiple random variables. And when we're adding multiple random variables together, we get this thing called the central limit theorem. And the central limit theorem says that the sum of multiple independent random variables approximates a normal distribution. And so that's interesting in this case, because what we're finding is that it appears that there's about a 12-day lag between infections and deaths. And that doesn't mean that, the slide says infections, but it really should say positive test. 12-day lag between positive tests being reported and deaths. And it doesn't mean that in any given case there's actually a 12-day lag. What it means is that as we add these multiple random variables together and the central limit theorem comes into play, that the mean of the distribution of how long it takes between a positive test result and death looks to be right about 12 days. And if you start looking at the daily data, especially aggregated at the national level, it's less apparent state by state, but aggregated at the national level, we appear to have this about a 12-day lag. And so that ends up being kind of a useful idea because it gives us some ability to look at the number of positive tests today and make some inferences about, or forecasts about what the death rate might be about 12 days from now. So, and in terms of calculating CFR, what that tells us is that in order to calculate a meaningful CFR, we should be taking basically the deaths today divided by the positive tests or infections from 12 days earlier. And so if we do that with the data that's available as of today, what we see is that we've got 54,000, I'm going to make my pen a little bit thinner here, 54,000 deaths today based on 636,000 positive tests or infections from 12 days ago. Now, that actually gives us a CFR of 8.6%. And I had said a minute ago that the CFR based on the junk CFR was 5.6%. But when we correct for the mistake of dividing today's deaths by, or total deaths as of today by the total positive tests as of today, when we correct for that mistake and divide by the deaths today divided by the total deaths as of today by the total positive infections as of 12 days ago, the CFR actually goes up. So we get an 8.6% with today's data. That looks worse. It looks like it's dramatically worse than what was reported out of Wuhan. It's way higher than 3.5%. It certainly doesn't match our intuitive sense of how deadly the disease should be, partly because of that anchoring effect. But the thing is, this number is now being calculated correctly, at least based on the available data, whereas the junk CFR number is not being calculated correctly. And I think one of the problems is that that junk CFR number is close enough to that anchoring effect number coming out of Wuhan that people haven't been very critical about it. But when we calculate it correctly now, it looks far enough off that maybe we're a little bit more open to being critical about it. And we're certainly not done picking apart this number yet. And so I'm going to come back to my theme for today, which is, do we know what we're talking about? And the first step is just using data from a relevant set of dates. So at least at this point, now we've got a relevant set of dates that we're talking about. And so that's a step in the right direction. The 8.6% CFR number looks high, but there are other problems that we're going to look at. And if I go back to my graph here on the left side of the screen, you can see I've tried to illustrate graphically the idea that the deaths for today are coming from the infections from the 12 days ago, approximately. And so we've still got the next 12 days of positive test results. There's got to be some additional deaths that come from those, even if we just totally turned off the positive tests or infections as of right now. We would still have a 12-day period approximately to work our way through. Okay, so second correction we need to make to this data is that positive tests and infections are not the same thing. They are not the same thing at all. I suspect at this point in time, we all know people who had symptoms who were turned away from testing, and that was a really big deal a month ago. It still continues to be a big deal even now. In Washington State, where I live, I do know some people who have been able to get tested, but I also know other people who were symptomatic who were told not to go in for testing. So there are people who are symptomatic who are told not to be tested. In addition, there are people who are asymptomatic who don't even think about getting tested. And the data on that, I think, is actually pretty consistent. We've got data from the Diamond Princess cruise ship, which is an interesting kind of almost controlled experiment because everybody was quarantined in place for quite a while. And then we've got data from Iceland, which is also interesting because it's they've done really a significant amount of testing of the population in Iceland. In both cases, they found that about 50% of the people who test positive are asymptomatic. I think there's probably some upward movement possible in that number too, because they're just testing people as of now who have the active virus and would test positive for the active virus test. That doesn't include the people who have previously been infected and have the antibodies, but are not currently positive. And we also have seen cases where even people with serious symptoms have been refused testing, and that's interesting too, because there are lots of reports, and you probably have heard them as much as I have, where somebody with pretty serious symptoms calls their doctor, and the doctor says, well, whether you test positive or not, we're going to recommend the same treatment for you at this point, so there's no real reason to get the test because we're going to recommend the same thing either way. So I think we have asymptomatic people, we have people with mild symptoms, we have people even with serious symptoms. Now, how would we account for that quantitatively? How would we account for the idea that the number of positive tests might be lower than the number of infections? Well, it turns out this has happened before. When we had H1N1 swine flu in 2009, it was pretty interesting because the initial pattern of concern about the deadliness of it was very similar, if not more so initially than COVID-19. And in the very early reports, as you can see from the chart on the left here, these are studies that are arranged chronologically. The estimated case fatality rates mostly varied from about 0.01% to 5%. So this is a huge variation. But there were additionally outliers that ranged from 0% to 13.5%. So this is just a massive variation in the different case fatality rates that scientists and researchers were predicting. And the ultimate value ended up at 0.02%. You can see that on the screen as the red dot on the far side of this graph. And so I'm going to show you another graph. This one shows the full range, including the outliers. You can see there's only one up here at 13.5%. So if we take out the 13 values that are greater than 1%, you can still see that there's quite a wide range of values, including many, many, many values that are really, really high compared to the ultimate value. And it turns out that the error in these case fatality rates mostly arose from counting only confirmed cases rather than trying to come up with some kind of estimate for infections. And this led to errors in estimating the case fatality rate of up to 500x. And I want to be clear, I'm not talking about 500%. I'm talking about an error of a factor of 500 times error in the estimate or initial estimate, some of the initial estimates for the case fatality rate of H1N1 swine flu. So again, I'll come back to my theme. Do we know what we're talking about? You know, if we're taking positive test data and thinking that that is the same as infection data, we really don't know what we're talking about. We're not clear what the subject is. And really, that's why in the graphs that I'm showing you, I'm pretty disciplined about labeling them as positive tests, not infections, not cases, because it really is what we know is the positive test number, and there's a lot behind that that we don't know. Okay, so what do we think the multiplier might be that converts the number of positive tests to number of infections? Well, we've got a couple of data points. And, you know, I like the idea of estimating by analogy, you know, seeing what's worked before. I like the idea of making use of historical data, which we have a little bit of from prior pandemics. So one data point we have is that the H1N1 estimates of infections versus test cases were off by as much as a factor of 500. Another data point we could consider is that for the annual flu in the US, about 150 people are infected for each one positive test. In other words, the multiplier would be 150x of the positive test number to get the number of people who actually have been sick. And then we had the interesting report yesterday out of New York State where Governor Cuomo in New York said that 25% of New York City is infected. And if you take the number of positive tests in New York City and divide that by or if you take the population of the number of people who are therefore infected in New York City, and you take the number of positive tests, that gives us a multiplier of 13x just based on the New York data. And that's, you know, that's as of yesterday. And the interesting thing about the New York data is they're now starting to do sampling with antibody tests. So it's not just people who are actively sick, but it's also people who have been sick. And with that antibody tests, when they did the test last week, I think they had 21.7% they said was infected, whereas yesterday they're now saying 25% is infected. So it'll be interesting to see as the days go by if that 25% number stays at 25%, or if possibly that number continues to go up. I mean, I think the anchoring effect could easily be coming into play on this number as well, where somebody can be sitting around saying, well, there's no way that, you know, more than 25% of people could be infected. They probably started out saying there's no way that more than 10% of people could be infected. And there could be things happening, I'll get to that in a minute, where there are places where you need some judgment or some gray areas, and then you get some bias creeping in from the anchoring effect, and that ends up fudging the number a little bit. It's not that anybody's doing it for sinister reasons, it's just human nature and the way people go about these kinds of things. So let's take a look at how many are really infected. And by that I mean coming up with some kind of estimation model. And you know, one of the things that's been interesting about the CFR number and the number of positive cases and so on, from my point of view as somebody who wrote a book on estimation, is there's not any notion of ranges in the vast majority of reports. There's no notion of uncertainty. Every number that's presented is presented as a single point number, as though, okay, here's the right number. And I think we would actually be pretty far ahead if we'd started out 2 or 3 months ago talking about uncertainty. Well, how much uncertainty is there on the low side of this number? How much uncertainty is there on the high side of this number? So here's my attempt to come up with some sort of guess, I'll say estimate, about how many people are really infected as opposed to the number who have tested positively. So if we look at the number of people who have only mild symptoms who don't get tested, there was a WHO report based on the Wuhan experience that said that 85% of the people who they tested positive had mild to moderate symptoms. So if we take that seriously, the idea that 85% have only mild to moderate symptoms, that implies only 15% are serious enough, maybe even to call and ask about being tested. The other 85% either just get turned away or don't even think about calling. So that gives me a multiplier, a nominal multiplier of 5 to multiply the number of test cases by 5 just based on the severity of the symptoms. And I'm going to say low is 3, although I honestly think that's too low. And high is 7. And 7 would say out of that WHO Wuhan study that all of the people who had mild to moderate symptoms don't get tested, all of them. So all 85% don't get tested. That would give us a multiplier of 7. So then I think I want to have a line for people who are not tested who do have serious symptoms, and that goes back really, that's just based on my personal experience. So this is kind of the softest number in here, I think, which is based on people I know who have had, and news reports I've read, but these are anecdotal only, that talk about people who have serious symptoms, and then the medical staff says, we treat you the same way whether you test positive or not, so you don't need to get tested. I know that there's some amount of that, so I'm saying the low end of that is 1.5. I'm making up a nominal number of 3. As I said, this is just based on reports, so there's some fuzziness in that number for sure, and a high number of 5. And then we've got the number of people who are asymptomatic, and I think that's actually a really interesting number as well. And I think that one's based on data from the Diamond Princess cruise ship and Iceland, where they found pretty darn close to 50% of people who test positive are asymptomatic. And so I've got a low multiplier here of 1.8, which basically says, what if it's 45% of people who test asymptomatic? And I've got a high, or rather 55%, sorry, what if 45% of people are asymptomatic? And I've got a high multiplier here that says, well, what if 45% of people are asymptomatic? So anyway, we multiply these numbers together, we get a total adjustment on the low side of 8, we get a nominal adjustment in the middle of 27, a high adjustment of 78, and that gives us, based on a number of positive tests as of today of 988,000 in the US, that gives us a range that goes from 8.1 million to 77 million in terms of possible infections. So in estimation, I would call this a cone of uncertainty. The cone of uncertainty is about future. This is actually about present, so I don't know if it's really a cone of uncertainty. It really is just error bars on the estimate, but a range of 8.1 million to 77 million possibly infected as of right now. If I was going to bet, my bet is that we're a lot closer to the high end of that number than the low end of that number. But and part of that is based on the fact that New York City's multiplier is 13, supposedly. And New York State has tested the highest percentage of its population of any state other than Rhode Island. So given that they have a relatively high test percentage and they have a 13x multiplier, a lot of the rest of the country has a lower, well, the entire rest of the country, except for Rhode Island, has a lower percentage of their population that they've tested, which suggests that the multiplier is probably higher for the people who are actually infected, higher than New York, which is at 13. So I like my 27 multiplier number pretty well, and would not be at all surprised. I'd be surprised if it's lower than that. I wouldn't be surprised if it's higher. Okay, so how does this affect the case fatality rate? Well, it affects it quite a bit, because if we take the number not from today, which is the 988,000 number, but we take the number from 12 days ago, and we multiply that by our various multipliers, we multiply it by 27. This should say 8. So if we multiply that by, what are we doing here? Let's see. No, okay. Oh, right, because it's 12 days earlier, so it's not 988,000. I was trying to do the math in my head and thinking, why is 8 times 988,000 5 million? But it's not times 988,000. It's times the number um, from 12 days ago. So if we take the deaths today divided by the infections, not positive tests, but infections that we calculate from positive tests from 12 days earlier, that would give us a high CFR of 1% and a low CFR of 0.1% with a nominal CFR of 0.3%. And so here I come back to my theme of saying, do we even know what we're talking about when we're putting out a single point number, but we're adjusting that single point number on a daily basis or a weekly basis? It's pretty clear that we don't know what that single point number really means. We probably ought to be talking about a range that has some uncertainty attached to it rather than a single point number. And I think this has been a common, not very constructive feature of a lot of the reports on this issue. All right, so now let's get a little bit stricter about our terminology. Case fatality rate, properly speaking, is about the number of people who have actually tested or been diagnosed as positive. There's another concept called IFR, or infection fatality rate, which refers to the total population that's actually infected. The final numbers that I was talking about a minute ago up here really would more properly be described as infection fatality rate rather than case fatality rate. It would be really nice if this terminology was used with some consistency, but from my reading, I have not found that it's used with any consistency at all, including in journal articles that look like they really should be fairly clear with their terminology. Even in the journal articles I've read, they confuse CFR and IFR, or they just never, more commonly, they just don't use the IFR expression. They only talk about CFR. Even when they're not talking about diagnosed cases, they're talking about some estimate for number of infections out in the wild somewhere. So again, back to the theme, do we know what we're talking about? Are we talking about CFR or IFR? And just as one interesting data point, for what it's worth, remember that I pointed out that with seasonal flu, only about 1 out of 150 people who actually has the flu gets tested for the flu. If we calculated the case fatality rate, not infection fatality rate, but case fatality rate for the flu, the same way that CFR is being calculated for COVID-19, the CFR for the seasonal flu would be about 18%. So it'd be an enormous number because the vast majority of people who have the flu don't actually get tested. So, so terminology makes a difference, and the CFR number, in a lot of senses, is actually, if we're literal about CFR, is not really a very interesting or relevant number. It's really more the IFR that we're really concerned with. Okay, so we've got a range for CFR. This seems like we're making some progress. Now the question is, does this range in CFR apply to you, or does it actually apply to anyone? And the interesting thing here is that because the mortality of COVID-19 varies so much by age, it really doesn't apply equally to everyone. So if I take, let's say that I take the mortality data, the COVID-19 mortality data from South Korea, and I'm doing that because they tested a relatively high percentage of their population. And you can see on this graph on the left that they basically had no fatalities under the age of 29. And then they had a very low fatality rate up to about age 50, started to tick up a little bit between 50 and 59, ticked up a little more between 60 and 69. And then by the time you get to 70 and 80, then the case fatality rate's actually pretty high. But the interesting thing about this is that when you take overall CFR number, so if I go back here and say, okay, I've got my range of CFR that goes from 1% down to 0.1%. Well, what does that really mean? If I take South Korea's data, the age breakdown of mortality by age, and I apply it to the population of my state, Washington State, I get an overall CFR number of 0.77%. So, and that's just based on taking the number of people in each age category, or the percentage of people in each age category, throwing it against the mortality rate in each age category, and coming up with an aggregate number. And so as you can see from the graph here, the average CFR is 0.77%. But if you look down the different age categories, there's no age group that actually has a CFR of 0.77%. People in their 50s have a CFR that's lower than that. Everybody under the age of 60 has a CFR lower than that. People over the age of 60 all have CFRs that are higher than that. That overall aggregate CFR number doesn't really tell you anything. It certainly doesn't tell you as an individual anything about what your risk is. It also doesn't really tell you anything unless you know where you are and what the demographics of your state are. So if I take, Italy has been in the news a lot because of the high death rate there. If I take South Korea's age breakdown mortality rate and I apply it to the Italian population based on their age breakdown, I get an overall average CFR for Italy of 1.28%. So Washington State's is 0.77%, Italy's is 1.28%, and that's just based on the fact that, on average, the population in Italy is older than the population in Washington State is. So it's the same disease in Italy as in Washington State. It's the same age-based mortality data in Italy as Washington State, but you get an overall CFR in Italy that's 66% higher than the overall CFR in Washington based on the exact same mortality data. And the difference is just demographics of the population. So now if we go back to what we're reading in the news about CFRs for different countries and so on, where it's just one number and there's no adjustment, and the vast majority of cases made for the age of the population in the country, this basically becomes a meaningless exercise, or at least it's an exercise with really high error bars because of the fact that the demographics vary. And this actually applies just as much inside the US as outside the US. It turns out that Washington State's median age of 38.0 is really close to the United States' median age overall of 38.2, but the range in the US is Utah has a median age of 31, Maine has a median age of 44.9. So if I were to take the South Korean mortality data and apply it to Utah, I would get an overall CFR less than 0.77 because Utah is younger than Washington on average. If I were to take that same mortality data and apply it to Maine, I would get a higher overall CFR because Maine's population on average is older than Washington's population. And so this really comes back to the idea of, do we know what we're talking about? If I were to say to you, software projects last 3 months and they require 20 staff months, and I was just to make a blanket statement, software projects are 3 months long and they take 20 staff months, you'd probably look at me like I had two heads or something, because the idea that all software projects take the same amount of time and require the same level of staffing doesn't make any sense. Well, the same basic idea applies to these overall CFR numbers, where it's not demographically adjusted, it's not adjusted for the age of the region that we're talking about. And even if it is, all it does is give us an aggregate number. It doesn't tell us anything about the risk factors for any individual. It's kind of meaningless in the same way. So comes back to the idea, do we really know what we're talking about? If we add a range, that's great. If we make it a real apples to apples comparison based on the dates we're talking about, that's great. We get our terminology cleaned up and talk about infection rate instead of case fatality rate, that helps. What we end up with is still a number that I think is of modest usefulness regardless. All right. So I want to turn now and talk a little bit about state level data in the US. And we are tending to see data like this. So I've got this site that I look at on Bing, bing.com. And this, I'm not picking on Bing per se, but I think this is a very average representation of how the data is being presented. We've got this list down the right side of the screen here that shows New York, New Jersey, Massachusetts, and so on. These are sorted by number of cases, raw number of cases, where it's just New York has the most cases, New Jersey, and by cases I mean positive tests. New York has the most positive tests, New Jersey has the second most positive tests, Massachusetts third, Illinois fourth, et cetera, et cetera. So, why would we do this? Well, and if I've shown graphically here, this is a chart that shows, well, I'm starting with, that was number of positive tests. This graph here is number of total deaths. And I've arranged the states basically from west to east because I think there's some interesting patterns that emerge when you do that. But you can see New York is way up here, New Jersey is down there, Michigan, Louisiana, and so on. And if we do the same thing, I would ask you as I talk through this to what happened here? Oh, to keep your eye on a few states: Connecticut, Rhode Island, Louisiana, Colorado, and California. So kind of keep your eye on those as we go through some permutations here, because there's some interesting things that get misrepresented if we don't account for the size of the state. So here's total deaths. And because, you know, all the states are clustered down here on the bottom and you can't really see what's what, then we see reports where people say, oh, well, let's put on a log scale. And now the states get spread out a little more. And now it really looks like, if we look at our state level data, it looks like Washington's pretty bad and California's pretty bad. And, you know, New York doesn't look as bad as it used to. It's still the worst, but, you know, now we've got Florida in here and Illinois and some other states like that. So I know log scale, depending on what we're looking at, probably not that useful. We do the same thing with total positive tests, where in this case, New York has almost 120,000 total positive tests. And we've got a whole bunch of states clustered down here at the bottom. And it kind of looks like maybe California is having some problems over here. Texas looks kind of iffy. Massachusetts looks kind of iffy. Rhode Island looks great. Colorado looks fine. Washington State looks, you know, kind of fine. Maybe not as bad as a lot of these other states. So the problem with all this is we're just talking about raw numbers. We don't have the same number of people in each of these states. And so when we talk about raw numbers, this is basically a proxy for how big the state is, you know, plus or minus some true variation in the infection rates and the death rates. So if instead we do, let's see, did I adjust that? So if instead we adjust per 100,000 population, the number of deaths, now we get a fairly different picture of what that looks like. You know, whereas before we saw California was up pretty high, now California is, I don't even know if I can find California. I think it's buried under one of these other markers. But, you know, Louisiana looks worse. Massachusetts is starting to look a little bit worse. Washington starts to look a little bit worse. New York is still the worst. New Jersey looks worse than it did before. And then if we look at positive test rate per 1,000 population, you know, now we start to see a little bit of a different picture than we did before too. We've got Washington State at 1 positive test per 1,000. We've got New York at 6 positive tests per 1,000. New Jersey, Louisiana, Michigan, Massachusetts, Connecticut, Rhode Island, and so on. So I think once we start looking at positive tests based that is normalized based on the population of the state, it gives us some different insight. We don't have that same big cluster of every state clustered down at the bottom of the graph. We actually have quite a bit of variation once we make the adjustment for population. And the idea that we keep reporting state level data and looking at state level data just as a raw number, you know, the idea that we would equal weight California as a very populous state, New York as a very populous state, directly compared to states like Washington, Colorado with relatively small state populations, you know, or Wyoming or Montana or South Dakota, just doesn't make any sense. So I think this brings us all back to the idea that if we go back to the idea of positive tests, we actually can get some useful forecasting capability out of here if we're actually clear in what we're talking about. So positive tests, we know, are a leading indicator because the positive test rate today, 12 days from now, gives us an idea of what the death rate is likely to be 12 days from now. So as long as we look at positive tests to start, we account for the 12-day lag between positive tests and death, then we can actually start to make some interesting inferences about what the future is going to look like. And so at the national level in the US, I'm looking at this US data right now, And to me, my marker is really fat there. Let's see. So to me, I'm looking at the positive test rate here. I'm not seeing any big decline in the U.S. data. And so to me, this says we got another 12 days, at least countrywide, likely of, this basically the same level of deaths we've had, because the test rate's not coming down. We've got a few days where it's coming down. I think we have tended to see in the data that some of the data gets adjusted upwards, because not every state reports in every day, and so we get a lag in, as sometimes the numbers from yesterday look low and then they get adjusted upwards. But overall, this looks pretty flat to me, and looks like we're going to be seeing the same thing we've been seeing for a while, unless we can get those positive test numbers down. And I think we can take this one step further, and we can go look at this by state. And so one thing that you may not know about me is that I am kind of an Excel Jedi master. So I've actually created this animated graph in Excel. What this is going to show you is this running 7-day average of positive tests per 1,000 population by state. So I'm going to go ahead and run that. And you can see Washington takes off, then Michigan takes off, now New York is taking off. New Jersey's kind of following New York. Michigan and Louisiana are taking off. New York is climbing way faster than anybody else, but Louisiana and New Jersey are way up there as well. Louisiana gets a grip on its problem and starts to be reducing the number of positive tests. New York follows and starts to reduce its positive tests. New Jersey is kind of hanging in there, not really improving that much. And this is the status as of yesterday, as of April 27th. There's kind of an interesting West Coast to East Coast pattern here, where the East Coast states on a per 1,000 population base are definitely experiencing a much higher rates of infection than the West Coast is. If you look at California over here, it's not really having much of a problem. Washington State, my state, was kind of the lead, unfortunately, nationally, but we got our situation pretty much under control. I'm looking at this graph saying, and then the line here shows, have they made progress? If there's no line, that means they're at their peak, basically. So Rhode Island is currently at its peak. Massachusetts currently at its peak. Connecticut peaked a little bit higher and has been coming down. New Jersey's come down a little bit. New York has come down a lot. Vermont, peaked pretty low, but they seem to have really gotten their situation under control. But these eastern states, there definitely is a cluster where we've got, basically most of the eastern states are higher than most of the western states in terms of positive tests. If I back this up a couple days, you can kind of see what's happening over time. Colorado opened up this week. I'm not supposed to stray into policy, but based on Colorado's numbers, well, let me just say this: Washington State's not opening up. Colorado is opening up. If I was going to pick one of those two states that was safe to open up, I would open Washington before I opened Colorado. It's also kind of interesting to look at these numbers and say, South Dakota has not had any policy in place for stay-at-home or anything like that, but these more sparsely populated western states just haven't had the same issues that the densely populated eastern states have had. Anyway, I think once we start, and then I guess the final thought here is keeping that 12-day lag in mind. We're going to continue to see we're likely to continue to see some deaths in these eastern states based on the fact that as of yesterday, we've got some fairly high positive test results still coming out of those eastern states. The western states, we're not seeing the same kind of issues. And I think to me, the poster child study here really is Louisiana, which started to get really high, but they took corrective action quite early on compared to, say, New York. Well, that's not really true. They took corrective action a few days before New York. So you start to see on April 8th, by the time they got to April 9th, Louisiana's number was trending down, 10th still down, 11th down. New York is still pretty much at its peak. Louisiana is going down significantly. By the time we get out to where we are now, they were under one positive test result per 1,000 population per week by April 16th. So whereas New York is still in the over 3.0 range. So anyway, that's what I've got in terms of prepared remarks, and I'm happy to take questions if there are any, or just have a conversation. Definitely not interested in talking about any political issues or policy issues, but anything having to do with data or numbers, I think, is fair game. So give you a chance to type questions into the chat if you'd like to. And otherwise, I hope you've found this to be interesting and have a little bit more clarity. I guess I should go back to my slide here and say that my overall message, the overall message really is be sure you understand what you're talking about. And again, as I said at the beginning, it's not about expertise. It's about even understanding what the words mean and what the numbers mean, which words attach to which numbers. And if all you've gotten out of today's session is a little bit more clarity about what you read in the news or see on the news, then I think it's been a worthwhile hour together. So go ahead and see if there are any questions. Make sure I'm looking at the right spot here. All right, so yeah, we got a question on analysis of IFR infection versus population density. So I think that, yeah, that question versus population density, yeah, so that's something that I haven't done. I think that's an interesting topic. It definitely looks like from this state level data, of course, the eastern states, in addition to many of them being more populous, are also more densely populated. New York State, for example, is actually a fairly large state in terms of the overall land area of the state, but the population is so clustered around New York City that it's as if the state were much smaller than it is in terms of population density. It does kind of look to me like, and this is not my area of expertise at all, but it does look to me like the more densely populated states are having issues. And I think New York is, in my mind, really the only city in the U.S. that has the kind of population density that you'd see in, say, China. And so to me, it seems like that's not probably just a coincidence that New York has had the biggest problem of in terms of the positive infections and unfortunately deaths. So yeah, that's an interesting thing to look at. I'm not quite sure how involved that would be, but I definitely think that's a good question. Yeah, so there's a question here of, is there any social distancing data? Would that be another factor for grouping the data? You can probably, based on your own reading of the news, take a look and see. I personally, just staring at it, I don't see any correlation here, but I don't think the states are the same in terms of their need for social distancing because of that population density question. It really does look like Washington State got on it pretty early. California got on the social distancing a little earlier than Washington did. California is a very populous state, but more spread out. People spend more time in their cars than they do on the subway, like they do in New York. So I don't know. Somebody else could take a look and try to apply social distancing and see what the effect has been. Again, I think Louisiana is kind of the interesting one. They ended up testing a really high percentage of their population, relatively speaking, and I can show you that that number for anyone who's still with me and curious. If I go through and sort by percentage of the population tested, you can see here, I don't know if those numbers are big enough. I'll make them bigger. So you can see Rhode Island has tested 4.8% of its population. New York 4, Massachusetts 3.26, Louisiana 2.99. Louisiana really got on this fairly quickly. It's kind of interesting. If you look at the percent of the population tested, it's pretty clear this has mostly been reactive after there has been a problem. So Rhode Island, New York, Massachusetts, Louisiana all started testing actively after they already had a problem. Utah has not had the same issues. North Dakota hasn't had the same issues. So that looks a little bit less reactive. And if I go over to my my state graph page here, got South Dakota over here is, it's not the best, but it's far from the worst. New Mexico is, let's see, where did New Mexico go? Oh, New Mexico is over here. So, they've basically were quite proactive in getting testing started. So, it's kind of interesting to see that, but my graph is messed up because I changed the sort order on my analysis page. So if I go back to the geographic sort, then then my graph should look more correct. So yeah, so now we've got New Mexico, not looks pretty good. So anyway, so yeah, so I think I haven't done anything in looking at social distancing, but looking at the testing, I think it's a little bit of a mix of states that got started late and have tested a lot versus states that started testing a little bit more proactively. But I think if you do a correlation, so I've got some correlation data here. So correlation with positive tests per 1,000, correlation with deaths per 100,000. So the percent of the population tested is actually, moderately correlated with the deaths per 100,000. It's actually one of the lowest correlations. One of the things that's interesting to me is the correlation between positive tests per 1,000 and deaths per 100,000 is 0.97, which in a way isn't surprising. You'd expect the positive tests and the deaths to not be to correlate with each other. But when you look at the percentage of tests that turn out to be positive, that varies state by state, that varies quite a lot. And so there's so much test variation across the states that I'm actually a little bit surprised that the correlation with the death rate between the test rate and the death rate is so high across the set of states, just because the test practices have varied so much. I kind of expect that not to be so strongly related. Yeah, so here's an interesting question. Early IHME estimates for 95% confidence were criticized when the actual values came in outside those intervals. But in the same article, it was said that had the intervals been wide enough to be accurate, they would have been useless for policymaking. Any comments? So, you could just change the words on this, and this would be a software estimation question easily. One of the points that I made in my estimation book and that I make when I teach the estimation class is that a wide range says you don't know what you're talking about. And if you don't know what you're talking about, you should use a wide range to communicate clearly that you don't know what you're talking about. So the IHME estimates, the idea that the intervals, if they'd been wide enough to be accurate, they would have been useless for policymaking. They should have made them wide enough to be accurate, so it was clear that they were useless for policymaking. I don't think there's any virtue in misleading policymakers about the accuracy of your data. So I think that's a pretty damning statement. And I'm just going on the question here, so don't quote me as that being an accurate report. But if this question is accurate, that this article says that if the intervals were wide enough to be accurate, they would have been useless for policymaking. I mean, that is a pretty damning comment. That it says the intervals may have been artificially narrowed, so they weren't actually 95% confidence intervals. And you saw the width of my intervals for the overall CFR here. I've got a factor of 10 variation in my meaningful range of CFRs. You'll notice the high end is still way below that 3.5% number that came out in the early Wuhan data. You know, is that, I don't know, is it too wide for policy making? I don't know, but I would rather have my policy be made on the basis of a clear picture, including a clear picture about how much uncertainty we're dealing with, rather than just made up numbers that tell the story that somebody wanted to tell, but that's not actually accurate. So interesting question, and certainly comes up in software estimation all the time as well. All right, I think that's about it for questions, and I guess we're actually out of time as well. So thanks for joining me, and have a good rest of your day.